Variable stars represent one of astronomy's most fascinating phenomena, providing crucial insights into stellar physics, cosmic distances, and galactic structure. These celestial objects, whose brightness fluctuates over time, serve as critical cosmic yardsticks and laboratories for understanding stellar evolution. This analysis examines the multifaceted approaches astronomers use to discover, classify, and analyze variable stars, from ancient observations to cutting-edge technology. Variable stars are defined as stars whose brightness as seen from Earth changes systematically over time. These luminosity variations can be detected through careful observation and follow specific patterns that help astronomers classify them. Variable stars fall into two fundamental categories based on the mechanism behind their brightness changes. Intrinsic variables experience actual changes in luminosity, often because the star physically expands and contracts, altering its energy output. Extrinsic variables, by contrast, appear to change in brightness when viewed from Earth due to external factors such as eclipse by a companion star or obscuration by dust. The variability magnitude differs significantly among stars. While some exhibit dramatic brightness fluctuations visible to the naked eye, others show subtle changes detectable only through precise instrumentation. Even our Sun demonstrates variability, with its energy output fluctuating by approximately 0.1% over its 11-year solar cycle. This underscores the reality that stellar variability exists on a spectrum, with most stars exhibiting at least some degree of luminosity variation over their lifetimes. The timescales of variability also span an enormous range. Some stars complete their brightness cycles in hours or days, while others may take months or years to progress through a single cycle of variation. This temporal diversity provides astronomers with different observational challenges and opportunities, requiring various observation strategies depending on the variability period being studied. The human recognition of variable stars dates back thousands of years, far predating modern astronomy. An ancient Egyptian calendar of lucky and unlucky days, composed approximately 3,200 years ago, may represent the oldest preserved historical document noting a variable star's discovery, specifically the eclipsing binary Algol. Indigenous astronomical knowledge also recognized stellar variability, with Aboriginal Australians observing and incorporating the brightness changes of Betelgeuse and Antares into oral traditions passed down through generations. The systematic study of variable stars in modern astronomy began in the early 17th century. In 1596, David Fabricius described a new star that later vanished from view. This same star was observed by Johannes Holvarda in 1638, who noticed that it reappeared and followed a cycle taking approximately 11 months. This star, later named Mira, became the first scientifically documented periodic variable star. The discovery challenged Aristotelian cosmology, which had maintained that the celestial realm was unchanging and perfect. Combined with observations of supernovae in 1572 and 1604, variable stars contributed significantly to the astronomical revolution that transformed our understanding of the cosmos. The second variable star described in astronomical literature was Algol, identified by Geminiano Montanari in 1669. However, it wasn't until 1784 that John Goodricke correctly explained its variability as resulting from a companion star periodically blocking its light, what we now recognize as an eclipsing binary system. Additional variable stars were gradually discovered in subsequent decades, including Chitini in 1686 and R Hydrae in 1704, expanding astronomers' awareness of these dynamic stellar objects. By 1786, 10 variable stars had been identified, establishing them as a distinct astronomical phenomenon worthy of systematic study. The classification of variable stars has evolved into a sophisticated system based on physical characteristics and behavior patterns. The primary division between intrinsic and extrinsic variables provides the foundation for more detailed categorization. Intrinsic variables, whose actual luminosity changes, include pulsating variables, eruptive variables, and cataclysmic variables. Extrinsic variables comprise eclipsing binaries and rotational variables. Among pulsating variables, Cepheid variables hold particular significance. These stars are divided into Type 1 and Type 2 Cepheids, distinguished by their population characteristics, light curve shapes, and period-luminosity relationships. Classical Cepheids are younger, more massive stars, typically found in the galactic disk, while Type 2 Cepheids are older, lower mass stars, often located in globular clusters and the galactic halo. This distinction is crucial because Cepheids serve as primary cosmic distance indicators through the period-luminosity relationship discovered by Henrietta Leavitt. Other important classifications include RR Lyrae stars, which pulsate with shorter periods than Cepheids and serve as standard candles for measuring distances within our galaxy. Additional categories encompass Beta Cephei, Delta Scuti, Gamma Doradus, Red Giants, and RV Tauri stars, each with distinctive characteristics in period, amplitude, and light curve shape. The classification process typically involves analyzing light curves, spectroscopic properties, and variability periods to determine the appropriate category for each variable star. Before the advent of modern technology, variable star discovery relied on methodical visual observation and painstaking comparison of star positions and brightness over time. Early astronomers maintained detailed star catalogs and compared the night sky against these records, noting any discrepancies in stellar positions or brightness. This labor-intensive process required extraordinary patience and meticulous documentation. The development of photography in the late 19th century revolutionized variable star discovery by enabling objective comparison of stellar fields over time. Several instrumental methods emerged for identifying variables from photographic plates. The blink comparator, famously used by Clyde Tombaugh to discover Pluto, became a primary tool for variable star detection. This device rapidly alternates between two photographs of the same sky region taken at different times, causing variable stars to appear to blink as their brightness changes between images. Other traditional techniques included the color contrast method, which utilized differently colored plates to highlight brightness variations, and the positive-negative method, which superimposed negative and positive images to identify inconsistencies. The Van Gent method, considered one of the most important empirical approaches, involved systematic examination of photographic plates to detect subtle changes in stellar brightness. Visual observation campaigns, often organized through astronomical societies, played a crucial role in monitoring known variables and discovering new ones. These efforts required standardized comparison stars with well-established magnitudes to ensure consistency across observations made by different individuals using various instruments. Contemporary variable star discovery has been transformed by advanced imaging technology and automated survey methods. Professional observatories now employ dedicated instruments and survey strategies specifically designed to detect stellar variability. CCD, charge-coupled device detectors, with their high sensitivity and photometric precision, enable astronomers to measure brightness variations as small as a few thousandths of a magnitude, revealing previously undetectable variables. Photometry forms the foundation of modern variable star observation, providing quantitative measurements of stellar brightness across different wavelengths. Multiband photometry, which observes stars through different color filters, helps astronomers determine temperature changes accompanying brightness variations. Time series photometry, consisting of sequential observations over hours, days, or years, produces light curves that reveal the pattern and periodicity of a star's variation. Spectrophotometry combines photometric measurements with spectral analysis, providing insights into both brightness changes and the underlying physical processes. This technique measures how the star's energy distribution across wavelengths changes throughout its variability cycle. Full spectroscopy offers the most detailed information, revealing how spectral lines shift and change as the star pulses, allowing astronomers to measure surface velocity changes through the Doppler effect. Space-based observatories have revolutionized variable star discovery by eliminating atmospheric interference and enabling continuous monitoring. Missions like Kepler and TESS, Transiting Exoplanet Survey Satellite, have discovered thousands of previously unknown variable stars, while providing unprecedented precision in light curve measurements. The Gaia mission has combined astrometric precision with photometric monitoring to create a comprehensive catalog of variable stars throughout the Milky Way. The light curve, a graph plotting a star's brightness against time, constitutes the primary analytical tool for studying variable stars. These curves reveal distinctive patterns that help astronomers identify the type of variability and extract key stellar parameters. The shape, amplitude, period, and features like secondary minima, or humps, provide crucial diagnostic information. Period determination represents a fundamental step in analyzing variable stars. Astronomers employ various mathematical techniques, including Fourier analysis, to identify the fundamental period and any harmonic components in the light curve. For stars with regular periodicity, like Cepheids or RR Lyrae variables, the period relates directly to physical properties such as luminosity, establishing the period-luminosity relationship that makes these stars valuable distance indicators. Light curve analysis also reveals amplitude information, the difference between maximum and minimum brightness. This amplitude varies dramatically between different variable types, from the subtle variations of some pulsating variables to the dramatic drops seen in eclipsing binaries or cataclysmic variables. The combination of period and amplitude often provides sufficient information to classify a newly discovered variable. Modern light curve analysis frequently incorporates statistical parameters beyond simple periodicity. Metrics like skewness, kurtosis, mean variance, and Stetson indices capture complex behaviors that simple period analysis might miss. These parameters prove particularly valuable for classifying irregular variables or distinguishing between similar variable types. Spectroscopy provides crucial insights into the physical mechanisms driving stellar variability by analyzing how a star's spectrum changes throughout its brightness cycle. For pulsating variables, spectroscopic observations reveal the expansion and contraction of the stellar atmosphere through Doppler shifts in spectral lines. As the star's surface moves toward Earth during contraction, lines shift toward the blue end of the spectrum. During expansion, they shift toward the red. This spectral analysis confirms that pulsating variables physically change size rather than merely experiencing surface phenomena. By measuring the velocity of the stellar surface throughout the pulsation cycle, astronomers can calculate the actual radius variation and better understand the pulsation mechanism. Combined with temperature information derived from spectral characteristics, these measurements provide a comprehensive view of how the star's physical properties evolve during each cycle. Spectroscopy also helps distinguish between different variability mechanisms. In eclipsing binaries, the spectrum reveals the presence of two different stellar components whose relative contribution changes during eclipses. For eruptive variables, spectral changes indicate temperature increases, emission line strengthening, or other signatures of outburst activity. Cataclysmic variables display dramatic spectral transformations that reflect the energetic processes occurring during their explosive events. The combination of spectroscopic and photometric data provides the most complete picture of variable star behavior. While photometry records the integrated light output changes, spectroscopy reveals the underlying physical processes driving those changes, making it essential for theoretical modeling and understanding stellar physics. The exponential growth in astronomical data from survey telescopes has necessitated automated approaches to variable star discovery and classification. Machine learning algorithms now play a pivotal role in sifting through terabytes of observational data to identify and categorize variable stars. These techniques can process thousands of light curves in minutes, performing tasks that would require years of human effort. Random forest classification models have emerged as particularly effective tools for variable star identification. These ensemble learning methods use multiple decision trees to classify stars based on features extracted from their light curves. Studies implementing random forest classifiers have achieved accuracy rates exceeding 86% in distinguishing between different variable star types like Beta Cephei, Delta Scuti, Gamma Doradus, red giants, RR Lyrae, and RV Tauri stars. Feature extraction constitutes a critical step in the machine learning pipeline. Algorithms extract both periodic and non-periodic characteristics from light curves, including period, amplitude, mean variance, skewness, kurtosis, and various statistical moments. Research indicates that period remains the most significant feature for classification, followed by mean variance and skew, with these three parameters providing substantial discriminatory power between different variable types. The Upsilon, automated classification for periodic variable stars. Using machine learning, software package exemplifies sophisticated approaches to automated classification. This system can identify variable stars regardless of their survey-specific characteristics, allowing application across different observational datasets. Similar frameworks continue to emerge, enhancing our ability to discover variables within sparse and noisy time series data. Confirming a genuine new variable star discovery requires methodical verification to ensure the observed variability is real and previously undocumented. The verification process begins with ruling out instrumental effects, environmental factors, or data processing artifacts that might mimic stellar variability. This includes checking for detector anomalies, atmospheric conditions, or software glitches that could create false signals. Once intrinsic variability is confirmed, astronomers must establish whether the star represents a new discovery by searching existing catalogs. The AAVSO's International Variable Star Index, VSX, serves as the primary reference, containing hundreds of thousands of known variable stars from multiple sources. This comprehensive database includes not only the general catalog of variable stars, but also variables identified through numerous surveys and individual discoveries. Secondary verification involves checking additional catalogs like the Guide Star Catalog or 2MASS, 2-micron all-sky survey, to determine if the object appears in other stellar databases but hasn't been recognized as variable. This step proves particularly important for high-amplitude variables like Miras or novae, which might be cataloged at different brightness states without their variability being noted. Precise astrometry represents another critical verification component. Accurate positional measurements, ideally to within an arcsecond, help ensure the variable hasn't been previously cataloged under slightly different coordinates. Modern digital imaging makes this precision readily achievable, eliminating many false discovery claims that resulted from positional uncertainties in earlier eras. The process of officially reporting a new variable star discovery follows established protocols within the astronomical community. After thorough verification confirms a genuine new variable, observers typically prepare a detailed report, including precise coordinates, magnitude range, estimated period, if applicable, light curve data, and classification evidence. This documentation provides the scientific foundation for recognizing the discovery. For variable star discoveries, the American Association of Variable Star Observers, AVSO, serves as a primary reporting channel. Their International Variable Star Index accepts submissions of new variables after verification through their review process. The submission requires comprehensive documentation, including finder charts, comparison star information, observational methodology, and data analysis techniques. Novae and supernovae, dramatic variables with significant scientific importance, follow expedited reporting procedures to enable rapid follow-up observations. Observers reporting these transient phenomena should immediately contact the Central Bureau for Astronomical Telegrams or similar alert systems to disseminate the discovery to the professional community. Time-critical spectroscopic follow-up often proves essential for understanding these explosive events. Publication in peer-reviewed journals represents the final step in documenting significant variable star discoveries. Journal articles typically include detailed analysis beyond basic discovery information, such as physical parameter estimation, evolutionary context, and theoretical interpretation. This peer-reviewed literature ensures discoveries become part of the permanent scientific record and receive appropriate recognition. Amateur astronomers make substantial contributions to variable star discovery and monitoring, forming a vital complement to professional efforts. The distributed nature of the amateur community enables continuous monitoring of variable stars across the globe, overcoming the time and resource limitations faced by professional observatories. Organizations like the AVSO coordinate these efforts, maintaining observation programs that have generated decades-long light curves for thousands of variable stars. The democratization of advanced imaging technology has dramatically enhanced amateur capabilities. Consumer-grade CCD cameras and computerized telescopes now enable amateur astronomers to perform precision photometry approaching professional standards. Software packages specially designed for variable star observation facilitate data acquisition, reduction, and analysis, allowing amateurs to produce publication-quality measurements. visual observation continues to play a valuable role, particularly for high-amplitude variables like Miras and certain cataclysmic variables. Using standardized comparison star sequences and observation protocols, experienced visual observers can achieve precision sufficient for meaningful scientific contribution. The accumulated visual observations in the AAVSO database represent an irreplaceable historical record spanning over a century. Amateurs frequently discover new variables while conducting systematic surveys of selected sky regions or through serendipitous observations during other projects. The most productive amateur variable star observers typically develop specialized knowledge and techniques focused on particular variable types or sky regions, allowing them to recognize subtle indications of previously undetected variability. Variable star research yields critical insights across multiple astronomical domains. Perhaps most famously, Cepheid variables serve as fundamental cosmic distance indicators through the period-luminosity relationship. This relationship, discovered by Henrietta Leavitt while studying Cepheids in the Small Magellanic Cloud, established that longer period Cepheids have higher intrinsic luminosity. Once calibrated, this relationship allows astronomers to determine distances by comparing a Cepheid's apparent brightness with its true luminosity derived from its period. Edwin Hubble utilized Cepheid variables to prove that spiral nebulae were actually distant galaxies beyond the Milky Way, fundamentally transforming our understanding of the universe's scale. Later, Cepheids provided crucial calibration for the cosmic distance ladder, enabling measurements that led to the discovery of cosmic expansion and eventually dark energy. Today, precise Cepheid observations continue to refine the Hubble constant, addressing tensions in cosmological models. Beyond cosmological applications, variable stars provide detailed information about stellar properties and evolution. Measurements of pulsation periods, combined with spectroscopic data, allow astronomers to determine stellar masses, radii, temperatures, and luminosities with remarkable precision. These observed properties provide critical tests for stellar evolution models and improve our understanding of a star's internal structure and energy transport mechanisms. Variable star observations also reveal population characteristics within our galaxy and others. Different types of variables are associated with specific stellar populations. Classical Cepheids with young disk populations, RR Lyrae stars with the halo and globular clusters, and Miras with the older disk population. Their distribution and properties provide insights into galactic structure, star formation history, and chemical evolution. The future of variable star discovery promises unprecedented depth and precision through emerging technologies and methodologies. Next-generation survey telescopes like the Vera C. Rubin Observatory will systematically observe the entire visible sky every few nights with exceptional sensitivity, potentially discovering millions of previously unknown variable stars. These comprehensive time-domain surveys will transform variable star astronomy from targeted studies to big data science. Space-based observatories continue to advance variable star research beyond atmospheric limitations. Future missions will combine high-precision photometry with advanced spectroscopic capabilities, enabling detailed characterization alongside discovery. Multi-wavelength observations, spanning from ultraviolet through infrared, will provide comprehensive views of variability mechanisms across different stellar types. Artificial intelligence and machine learning technologies will increasingly automate the discovery, classification, and analysis processes. Advanced neural networks capable of identifying subtle patterns in noisy data will detect variability that current methods might miss. These systems will evolve beyond simple classification to provide physical parameter estimation and anomaly detection, identifying truly unusual variables worthy of focused investigation. Collaborative approaches combining professional and amateur efforts will continue expanding our knowledge of variable stars. Centralized databases integrating observations from multiple sources will create unprecedented temporal coverage, revealing long-term behaviors and rare events. Public science initiatives will engage broader participation while maintaining rigorous standards through automated quality control and standardized methodologies. The discovery of variable stars represents a fascinating blend of historical perspective, observational technique, and technological innovation. From ancient observations noted in calendars to modern machine learning algorithms sifting through terabytes of data, our approach to finding these cosmic beacons has evolved dramatically, while their scientific importance has only increased. Variable stars continue to serve as crucial tools for understanding stellar physics, cosmic distances, and galactic structure. The process of variable star discovery has transformed from individual visual observations to automated surveys capable of monitoring millions of stars simultaneously. Yet the fundamental principles remain: detecting brightness changes, measuring their characteristics, and interpreting their physical significance. This continuity connects modern researchers with generations of astronomers who have contributed to our understanding of stellar variability. As technology advances, our capacity to discover and analyze variable stars will continue expanding, revealing ever more subtle variations and rare phenomena. The variable star population we know today likely represents just a fraction of what exists, with millions more awaiting discovery. These future discoveries promise new insights into stellar evolution, galactic structure, and cosmic history, ensuring that variable stars remain at the forefront of astronomical research for generations to come.